In the last section, we had this problem where new parents wanted to establish a college fund for their child, and the question was how much money should they deposit now so that if it compounds over the course of 17 years, it's a certain amount of money in the future. I believe in that problem it was $80,000. Well, what if we want to make it a little bit more complicated? Instead of depositing the money all at once, what if we establish a series of payments? So every year we're depositing a certain amount of money in the hopes that after 17 years, the future value will be, $80,000 or whatever we wanted. Well, this is quite a bit more complicated because only the first deposit that you make is going to compound for that full 17 years, right? Maybe you make another deposit after another year, well that second deposit is only going to compound for 16 years. And then your third deposit a year later will only compound for 15 years. So you don't have quite the same amount of compound interest on every single deposit. This is a much more complicated problem. And to answer this, in comes section 3.3, future value of an annuity. So for starters, an annuity is just any sequence of equal periodic payments. And we're going to be looking at a particular type of annuity, an ordinary annuity. So when the payments are made at the end of each time interval, where this is an ordinary annuity. And the question we're going to look at for starters is one very much like the one I just posed with the college fund. Is let's say suppose you decide to deposit $100 every 6 months into an account that pays 10% compounded semi-annually. So you're making payments you're making semi-annual payments, and it's compounding 10% semi-annually. The question is, if you make 6 deposits, so 3 years worth of deposits, how much money is in the account after 3 years? So what I'm going to do here is I'm going to build a timeline. I'm going to build a timeline so we can think about exactly what's happening to every single deposit. Unfortunately, I need more space on the board, so let me erase this and I'll be right back with you. Okay, so here I've got this simple timeline built up. I've got up top I've got years, 0, we started now, so 0 years, 1 year, 2 years, 3 years. And then the number of periods we have, the number of compounding periods and the number of periods in which we deposit money. So we've got 0, 1, 2, 3, 4, 5, and 6, right? Because we're looking at semi-annual periods. So we come in and the first period we say we're going to deposit $100. Deposit $100. Well, what's the future value of that $100? Let's think about this for a second. Bring it all the way down here. $100, it's going to compound, right? So it's going to compound, and after one period, we've compounded it once. So I believe our annual interest rate was 10%. So the rate per period is 5% because this is semi-annual. So we're looking at $100, but it's compounded how many times? 1, 2, 3, 4, 5. At the end of 6 years, it's compounded 5 times. So at the end of 6 years, this is the future value of this money, or sorry, at the end of 6 periods, at the end of 3 years, the future value of this money is going to be 100 times 1.05, the interest rate per period, to the power of 5. All right, remember we've got this simple formula for compound interest. A is P times 1 plus I to the n. All right, so the rate per period here, if the annual rate is 10%, the rate per period is 5%. So 1.05, number of compounding periods to the power of 5. Then second period, we come ahead and we say we're going to deposit $100. Well, what's the future value of this money? Pretty much the same thing, 100, but in this case, it only compounds 1, 2, 3, 4 times. All right, so the future value of this money is 100 times 1.05 to the power of 4. And hopefully I have enough space here, but we'll keep playing this game. Third period, we deposit $100. Future value of this money is 100 times 1.05 to the power of 3. It only compounds 3 times in this case. Fourth period, we deposit $100. You can see where I'm going with this, so I'm just going to keep filling it out. 100 times 1.05 squared. Fifth period, we deposit $100. 100 times 1.05 to the power of 1. This guy only gets to compound once. And then finally, sixth period, we deposit $100. It never compounds. 1.05 to the 0 if you want, but that's just 100 times 1. So this is the future value of each deposit. So as you would expect, the $100 that I originally deposit is worth more than the later deposits of $100. But the question was, what's the future value of the account? Well, the future value of the account would be the sum of all of the future values of every single deposit, right? So the future value of the account is the sum of all of these things. It's 100 plus 100 times 1.05 to the power of 1 plus 100 times 1.05 squared plus, I'm going to run out of space, so I'm just going to dot these out, plus dot 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 plus 100 times 1.05 to the power of 5. So you could plug this into a calculator, you could work this out, but of course this is kind of tedious, right? This is a little bit tedious, and if we had many more periods, suppose we had hundreds of compounding periods, it would be really tedious. So what's happening here is mathematically, this is called a finite geometric series, where every single term in the sum is just 100 times this 1.05 expression. So to get the second term, I'm multiplying by 1.05. To get the third term, I multiply by 1.05 again. To get the fourth term, I multiply by 1.05 again. So this is a finite geometric series, and there's a mathematical formula for handling this. If you want to see this in the textbook, it's all there. Go ahead and read through about geometric series. But I'm just going to give you the answer. I'm going to give you the formula for future value of an ordinary annuity. So here it is. Here's the formula for what we were just doing. It's the formula for future value of an ordinary annuity. It's given by FV, so FV for future value is what we're trying to compute, is equal to PMT. PMT is not three separate things. PMT just stands for payment. It's the periodic payment you're making. In the last example, that was $100 every $100 semi-annually. PMT, the payment times 1 plus I to the n. I is exactly as before. I tend to stray away from it though, but I is the rate per period, so in the last section I was usually calling that R over M, the annual rate divided by the number of periods per year. We're going to go with I here though, because it makes the formula a bit cleaner. 1 plus I to the n. N is the total number of periods, so that would just be, in the last section I was calling that M times T, so that's all that N is. 1 plus I to the n minus 1 divided by I. And this is coming from applying to that geometric series formula for the sum of a geometric series, but this is the end result. This is the formula for the future value of an ordinary annuity. So what we're going to do here, the first problem is one like we were just doing, where we're computing future value, but you'll see other problems where you'll be asked to solve for any one of these four unknowns. So you'll be given 3 of these things and asked to solve for the 4th. So let's see, let's do an example. So our first example is one just like the one we were looking at the beginning of this class, which is what's the value of an annuity at the end of 10 years if $1,000 is deposited every month into an account that earns 8% compounded monthly. So what do we have to do? Well, we just have to use our future value formula. So future value is PMT times 1 plus I to the n minus 1 all over I. We are given 3 of these things, and we're just asked to find the future value. So we just have to plug in. So future value is the periodic payment. We're depositing $1,000, so PMT is 1,000. We've got 1 plus I. What is I? So our annual rate is 8%, but we're compounding monthly, so there's 12 periods per year. So 8% is 0.08 divided by 12, because 12 months in a year. Minus 1. Oops, I forgot n. How many total periods do we have? Well, we've got 12 per year times 10 years would be 120 total periods. Right, it's 12 times 10, 12 per year times 10 years. Minus 1 over I once again, so over 0.08 divided by 12. And you plug this all into a calculator. Again, be careful not to round until the very end, but plug this all into a calculator, and I get, well, for starters, what would be a reasonable number? Just to check, make sure that your answer is reasonable. How much money have I actually deposited? We've got 10 years, every single month, so 120 deposits total of $1,000. So I'm expecting at least $120,000. It should be more than $120,000 because we've got all this compound interest going on. But if I have something less than $120,000, I've definitely made a mistake in my calculations, right? But if you plug this into a calculator, you get, this is $182,946.04. So a reasonable looking answer, which is quite nice, right? Because we only deposited actually 120,000, but after 10 years, we're looking at this figure instead. By the way, what's the total interest earned? Well, again, we've actually deposited 120,000. So if you were asked what's the actual interest earned, well, it would be this number minus 120,000 that we actually deposited. So the difference here would be 62,946.04. So we're gonna do another example. It's gonna be an example of a sinking fund, so a fund that's established to meet some sort of future obligation. And the question is going to be instead, we want to have some future value, so the future value is gonna be given. The question is, what's our payment size gotta be in order to hit that future value in a given time frame? So in comes the very first question from this section is another college fund. So parents have set up a sinking fund, again just a fund to meet some sort of future obligation, some future debt. Parents have set up a sinking fund in order to have $120,000 in 15 years for their child's college education. The question is, how much should be paid semi-annually into this account that pays 6.8% that's compounding, again, semi-annually? Well, this is an example of an annuity, so we're just going to use our future value formula. Future value is periodic payment times 1 plus I to the n minus 1 over I. We are given 3 of these values, and the question is find the payment size. So before I start plugging things in, and I don't always do this, sometimes I plug things in first, but how about we solve for payment first? So payment is going to be, what do I have to do? I have to multiply both sides by I. So I'm going to have I times future value. And then I have to divide by, oops. How about I not try to skip all the steps? Let's go I times future value is payment times, oh yeah, this would have worked. 1 plus I to the n minus 1. Alright, so all I've done here is I multiply both sides by I. So now if I want to isolate payment, and I'm going to write it on this side, payment is I times future value over, divide by this entire expression. 1 plus I to the n minus 1. So there is the formula rearranged for the periodic payment size. All I have to do now is plug in these expressions, or plug in these values. So payment size is going to be what? We have 6.8%, but it's compounded semi-annually, so I is going to be 6.8% is 0.068 divided by 2. So what is that? 0.034 times future value. We want our future value to be 120,000. Divided by 1 plus I, so once again 0.068 over 2 to the power of n. So what's n? We're going 15 years total, and we compound twice per year. So 15 times 2, n should be 30. 30 total compounding periods, minus 1. And we plug this all into a calculator. Again, careful not to round anything until the end, but plugging this into a calculator and rounding to the nearest cent, I get 2,363.07. So this is the payment size. This is how much you want to deposit every 6 months into this account at this particular annual rate, so that after 15 years you will have $120,000 total. Kind of cool, because these are not easy problems, right? Mathematically, if you think about how everything compounds in all of the compounding periods, it's obviously not an easy problem. But the fact that it boils down to really just using this formula makes it not that makes it much more manageable, I should say. So one of the hardest things to do is, given this formula, we've done one example where we solve for future value, one example where we solve for payment, but there's of course other variables in here too, right? There's I and n. Of course, the hardest thing to do is always solve for the time n, because just because it's stuck in the exponent, which means you have to use logs to isolate n in this expression. So I want to do one example of that, but I'm going to put it off to the next section, because the next section is very similar. So in the next section we'll have a similar formula, and we'll do an example where we solve for n. Okay.